with transportation problem, and we had discussed the first part of the transportation problem in the last week. I hope we were all able to understand how the problem is formulated as a linear programming problem, and we covered one of the network flow problems, that is the transportation. Today we'll see two more problems which are type of the network flow problem. One is the transshipment and the other is assignment, because we need to understand the formulation, right? So because that is the most important part of the management science problems, because if we can formulate and the problem and create the model correctly, then we can easily find the solution by using either manual methods or computer method. So what we did in the last week was one type of transportation as a network flow problem, which is the transportation problem. But it's a very common transportation problem is a very common name. So we normally try to learn them as a topic, transportation problem, although transportation problem is a type of network flow problem. We also learned in the last class that this is a type of linear programming problem. The only difference is in the formulation, that this type of a problem deals with something like a network where there are sources and destinations, and there are essentially two types of constraints, the supply and the demand constraints. In the transportation, we saw that there are many sources and many destinations, and the decision variable is how many, what should be the quantity of items to be transported from the different sources to different destinations to minimize the transportation cost. So the other two types of problem are the similar, but there are some differences. So those differences may confuse students in their formulations. So we will see what these problems are and how the formulation is done, how the modeling will be done. So let's begin with the first type, that is the transshipment problem, and then we'll see the assignment problem, and then finally we'll see a case study from book based on the application of transportation problem in the real situation, and then we'll understand what benefits does transportation method, the network flow problem or linear programming method will help in solving a problem of moving the goods from one place to the other, or assigning a group of goods or people to a particular task. Okay, so these are the three topics we are going to cover today. So the after the transportation method, we now have the transshipment model. So what is it? How is it different, and where does it come from? So we have to be careful. Okay, we have to be very careful while we get the problem on network flow to identify whether it is an assignment problem or a transportation problem or a transshipment problem. In a transshipment problem, what we see is that it is an extension of the transportation model. So if transportation model was S1, S2, S3, and there were different destinations to send the products from, this was how it looked like, and we have to find the best route to minimize the cost. In the transshipment model, there is an intermediate transshipment points. There is an intermediate transshipment point added between the sources and destination. So that means these become, we may say, if they become intermediate, or we have an extension here. So there are 2 more points or 3 more points which are before this network, like A1 and A2, and from here it may be more. I'm just taking 2, so just for an example. So there are 2 more points from where the product is coming first to S1, and then it moves to D1. So we first store here the product. Suppose this is the factory, and this is the storage, and this is the market, this is the destination. So what happens? The goods are sent from the factory A1 to store S1, and from the S1 the goods are sent to the markets, as we did in the transportation. So in the transportation only this component was there, but in transshipment there is an addition. The goods are coming from the factory and first getting stored. So there are 3 points. In the transportation there was just supply center and the demand center. In the transshipment there is an intermediate point as well. Okay, so it goes like this: A1 to S1, A1 to S2, A1 to S3, and then from A2 to S1, A2 to S1, S2, and A2 to S3. It doesn't go directly. Okay, so it is through these stores. So these factories, the product is the same. The product is the same. The supply from this side, in order to ensure that the problem is, we can solve the problem, we need to check whether it is balanced or not. So supply here at factory has to be equal to the demand here. And what is the role here of this? What will happen here? It has to be the same. All the supply which are coming here will be the same. The same supply will come here, and they will have to send the same demand this side. Okay, so there is not much change. There is only one extension in the transshipment model, and is that the one extra level is added in the transportation, and that is, there is a factory from where the products are coming to first, and a storehouse or a distribution center, and then it goes to the final market or retail outlets, whatever. Okay, so in our terms we call them the supply center and the demand center. Okay, so this is what transshipment model is. Is it clear to all of you? I mean, this is easy, right? It normally, this is what happens in a real business situation, that there is a factory, then from the factory the finished goods come first to a place where they are stored, and from there they are sent to different markets or retail outlets or different destinations. So that problem will look like this, as we see, just draw. Okay, so let's look at the problem from the book and how it has changed. In the book, the good thing is it has taken the same example. and it is moving on from the same example that we discussed in the transportation, and it is showing how the transportation problem has got transformed into a transshipment model. So what has changed here? Till this point, we already saw last week in the transportation model that there are 3 supply centers and there are 3 demand centers. The wheat was being transported from these centers to these centers, and we had to find out what is the minimum transportation cost, what may be the minimum transportation cost by selecting the different alternatives. We formulated the model and the equations were ready. But now in the new type of a problem, there is an extension. Okay, so what they have done, they have changed the numbers. This is 3, 4, 5 and 6, 7, 8. We start from another 2 sources, origins. Here what happens is there are 2 main centers, main supply centers, from where the wheat is coming, and these are just the elevators, grain elevators. So the first thing is, the first movement is from the supply centers to the grain elevators, and from the grain elevators they go to the flour mills, or in simple words, the demand centers. So we may say the supply centers, the demand centers, and the intermediate center. Okay, this may be easy to understand. Let me just check with you all. Is it clear so far? Can you please confirm on the WhatsApp group? Is it clear to all of you? How is it different from the transportation problem? And it's similar, but the only thing is it is an extension of the transportation problem. In the transportation, there were the supply centers and we just saw this part. But in the transshipment model, there is an extension of 2 more points on the supply side, and now there is a supply center, there is an intermediate point, and there is the demand center. So in the case of addition of 2 new centers on the supply side, the details or parameters are given. Till here the parameters were already given in the transportation model. These are the transportation costs from Kansas to Chicago. Is my voice clear to all of you? And you can see the screen, okay? Is it easy for you to understand? Or you want me to repeat? Can we go forward? Okay. Good. Okay. Thank you. Thanks for responding. Okay. So these were the transportation costs. So it's easy for us to understand that here also, this is $16 per ton of transportation, of wheat from Nebraska city to Kansas. So there are the 2 supply centers are now in Colorado and Nebraska, and the cost of transportation is given. Cost of transportation is given. It's here, the transportation chart, and this is what we needed to formulate the new problem, the transshipment problem. So 16, 15, 10, 14, 12 and 17. These are here in the chart also, and they have added it in the network. So with this, the problem is ready. The problem has been formulated. Now the question comes, how to create the linear programming equations for this problem now. Okay, so first of all, we need to check whether the problem is balanced or not, isn't it? For example, here last time in the transportation we had the these, 175, 150, 125, and we knew that both sides were 600. But now we see that this just plays the role of an intermediary. Okay, this plays the role of an intermediary. So they have to send from Nebraska. It has to come to the three centers first, and then it will go to Chicago, St. Louis, and Cincinnati. And the demand has to be kept in mind, the demand constraint. Similarly, from Colorado, first they will have to come to Kansas, Omaha, and Des Moines. So for this problem, there will be that supply-demand constraint, and then from here there will be a supply-demand constraint. So there is just an addition of new set of constraints in this problem. Okay, so let's see how to formulate. I have taken all parts from the book so that you can later refer to. So it's all of this is from the book. Okay, so you can check in the book from page number 233 to 252. This should be in the later pages. Okay, so as with the transportation problem, a linear programming model is developed with supply and demand constraints. So first of all, the available supply constraints from the farms in Nebraska. So let's look at, so X is what? X is the number of tons that we want to, we don't know, it's a variable, okay, it's a question mark. We need to find through the transportation or transshipment linear programming method. We have to find how many tons of wheat we should transport from one center to the other to minimize the cost. So X is the number of tons, 13 is the route, so 13, 14, 15, and 23, 24, 25. So this is the constraint on the first side, this one. So X1, this is X13, 14, 15. Okay, so let's see, is it here? Yes, 13, 14, 15. And what should be the maximum? It cannot go beyond that. That's 300, because this is the maximum. This is the maximum Nebraska can send. So in total, this has to be 300 only. What about Colorado? Again, Colorado can also send 300 tons of wheat. So we will have to write the equations accordingly. The equation is X, but the routes have changed: 23, 24, and 25. Let's look in the network. How does it look like? 2, 3, 2, 4, and 2, 5. All these X12, X23, X24, and X25 total should be 300, not more than 300. Okay, so this is one side of the constraint equation. Now we have to write the other side of the constraint equation. So here what happens? Here we have the same 36, 37, 38, 46, 47, 48, 56, 57, 58. Now what are the constraints here? 200, 100, and 300. So no matter which route we follow, we have to ensure that this constraint is satisfied. So first route is from Kansas to Chicago, Kansas to St. Louis, and Kansas to Cincinnati. So X36, X46, and X56, it has to be 200. Then the second option from X37, 47, 57, and the maximum that is required there at this center, that means St. Louis center, is 100. X38, X48, X58. The maximum that is required at Cincinnati is 300. So these are the two ends, two parts we have solved. One is this one, supply side, and the demand side. What about the intermediate side? We have to write equations for them also. So that is the new thing we have to learn. So you have to pay attention. So far, is it clear? I mean, you understood how the extended Rahaf asks, please again root numbers. Okay, I'll repeat again. So what I'll do, I'll first remove the red ones so that it's again clear. I'll repeat it. Yeah, please ask. Okay, because this is very important to understand. Here, it's given in the network form, but in the exams, maybe you don't get in the network, you have to create it. Okay, so first of all, you tell me, what is new in this problem, in the transshipment problem? Rahaf or any student, can you tell what is new in this problem? What is different from transportation problem? Very good. Yes, Ruba. Very good. So, what we see here, or in simple words, very simple words, we will say that instead of just supply and demand centers, there are three centers. Instead of two centers, there are three centers, or 3 points in this problem, 3 transportation points. This is the supply, this is the demand, and this is the intermediate point, okay, intermediate center. So that's clear to all of you. So what we did in the last class, we saw the supply and demand only, and we formulated the equation accordingly. But today, we have to see how this extension will have to be accommodated in the equation. So this extension is, now what happened, there are 2 supply centers, one at Nebraska and the other at Colorado. And again, the decision alternatives we have to explore all alternatives, isn't it? So like here, the minimum number of choice for the manager was 3, because she has to explore at least 3. But when we are using the linear programming formulation, we have to consider all possible alternatives. Then only our result will be optimum. So we have to consider all alternatives which are available. So here we understood last week, these are the possible alternatives, 3, 6. Okay, so these are the, what are these? These are the routes. These are the routes. So if I transport 200 tons of wheat from Kansas to Chicago, how much total will I pay? $1,200 total, isn't it? So we have to understand this. So when we solve the problem, this is what we are going to get. So if I transport all 200 from Kansas to Chicago, I get $1,200. Although this is not possible because Kansas City will have all its own constraint also. We saw in the last week that Kansas can only send 150. So that was the constraint in that problem. But here, then this is 100. So 4 to 7. So these are the routes. Now in the new form, when we have 2 more centers, the possible routes are 1 to 3. 1, 3. This is one route. If I send the wheat from this route, how much I pay? $16 for 1 ton. Then if I send from 1 to 4, I pay $10 per ton for 1 ton. And if I send from Nebraska to Des Moines, that is the third route, I pay $12 per ton. I don't know now how much is my X. Okay, I don't know what is the number, so I will have to write X16, X13, X14, and X15. So these are my 3 alternatives: X13, X14, and X15. These are 3 alternatives from Nebraska Center. Why 3 alternatives only? Because there are 3 destinations, only 3 intermediate points are there. Then coming to the Colorado Center, again, we see that there are 3 alternatives. I don't know which to choose right now, so I have to include them in my problem. One is 2 3. This is 2 3. So if I send from Colorado to Kansas, this route number is 2 3. Okay, and if I want to know how much will be the number of tons I want to send from Colorado to Kansas, I call it X from route number 2 3, that is 2 3, X 2 3, and if I send from here, I pay $15 per ton. Now coming from Colorado to Omaha, if I send from here from 2 to 4, so this route is 2 and 4. Here the cost is $14, and from 2 to 5 the cost is $17. So again we have three options: X 2 3, X 2 4, and X 2 5. This is on the supply side. In the demand side, this is already we have done it. X, now the numbers are 3 6, X 3 7. So if you have your notebook, try to write it yourself. These numbers: X 3 8, 3 6, 3 7, 3 8. Then you will better understand when you do it yourself. Then X 4 6, X 4 7, and X 4 8. Now these are X 5 6, X 5 7, and X 5 8. It's simple. It's very easy to understand. The only thing is we have to not lose concentration. Otherwise, it gets messed up. So we have to be focused. Is it clear? The route numbers, Rahaf? Okay, Rahaf asked, so if I send the product by 1-3 Chicago, 1-3 you mean Nebraska to Kansas. Okay, so this is one route from the supply center till intermediate point. But then after that, there are three more alternatives. So we have to look at this problem in two parts. Okay, two parts. This is supply center, this is intermediate point, and this is the demand center. Okay, so we have two parts. One part is from supply to intermediate, and the other part is intermediate to demand. So we have to see them into these two parts, intermediate to demand. Okay, so we don't mess up, we don't mix both of them. We have to see that the wheat which is produced at Nebraska has to reach any of these three. Okay, they have to reach these three. It may come from Nebraska or from Colorado. Okay, it doesn't matter. The main point is to minimize the cost. So we'll have to check which route is the best by formulating the model. So the first part is the supply center to the intermediate, and the other part is from intermediate to the demand. Okay, so X13 is the route from supply center to intermediate. Then once the wheat has come to Kansas, Omaha, and Des Moines, now the challenge is to, again, the question comes, the same problem which we faced last week in the transportation, that now it has to be again transported from here to these three centers. So we have to consider the second part of the problem, which one to choose from the 9 alternatives. So if we say I to D is 9 alternatives, and S to I are how many alternatives? Who will tell? How many possible alternatives are there from S to I, supply to intermediate? I to D we saw in the last week, from these three to these three. There were 9 decision alternatives. Okay, so tell me, I'm asking you a question, from the supply side to intermediate in this problem, how many alternatives are there from Nebraska, Colorado to these three cities? Then it will be clear, I'll be sure that you have understood. Fast, do it fast. How many choices are there for the supply chain manager to decide for sending the wheat from these two supply centers to these three intermediate? What do you have to do? Count the arrows. Very good. Mashallah. Lamia, good. Good. Okay. So all of you got the idea? We have to count the arrows, because that's the good thing about the making the network, making a picture of the network, that we can see what are the number of routes available to us, and then decide on the cost, the route. Okay, so we, in this problem, in this part, from supply center to the intermediate point, we have 6 alternatives, and from the intermediate point to the distribution the demand center, there are 9 points that we saw in the last week. Now what we have done, we have already created the equations, or we created the model for the supply side and the demand side. Okay, the supply side and the demand side. Let's look at it. Supply side is from this one. We have created the equations from supply to intermediate, and we have created the equation from intermediate to demand. All right. So the thing missing now is, what about I, the point at I? I, what is I? I is the centers number 3, 4, and 5. Means the centers at Kansas, Omaha, and Des Moines. Those who fall in between, how to write the equation there? That is the main challenge in this problem. Okay, so this is easy. This formulation was easy, like right till here. We had already done it in the last week. We don't have to confuse with the intermediate, because we have to look at the problem in 2 parts. One, the supply side, so we have 6 options. In the demand side, we have 9 options. So we wrote down all the 9. How many should be there? These are 6, and there it is 9. So we look at it. The problem here, x, 2 alternative, x13, x14, x15, 300 on the supply side. So these are the possible costs, and number of, not possible costs, these are the number of tons we can send from Nebraska. And what is the constraint here? The constraint is 300. Then this is the second one. So in total there are 6 alternatives. Now coming to here, the demand side, there are how many alternatives? 3 alternatives and 9 alternatives. X36, X46, 56, 37, 47, 57, 38, 48, 58, and these are the demand maximum constraints. So we total have 9 and 6, 15. Now this is very clear. I hope no student has any problem in understanding these 2 set of equations, one the supply and the other demand. Is it okay? So we can move to the second one. Total 600. Yeah, I'm saying about the number of routes. Okay, so number of routes on the supply side are 6. Number of alternative routes, and number of alternative routes on the demand side, it's 9. So total, the manager has 15 alternatives, and that means in these equations there should be 15x. So that is, these are there, x, if you count these routes, there are 15 routes in total equations. Okay, now can we move to the next part, the transshipment point or the intermediate point? This is the tricky part in this problem. All right, so this is what makes it different, and now I have to focus on understanding the how equations have to be written here. Okay, so let's look at the problem again. First of all, we saw that while writing the supply and demand constraints, we have to simply look at it from 2 angles, one in 2 parts, SI and ID. But when we come to the intermediate point, we have to look from both sides, from the supply side and from the, what happened? Sorry. The supply side as well as the demand side, from supply and demand. So how to do that? So let's read, what is the method of doing it. So it says, we must develop constraints for the grain elevators, the intermediate points, or more technically, that is the transshipment point. So we now understand, the technical name. The transshipment means it is the intermediate. For example, Dubai, Dubai is an intermediate point. It's a hub of transportation, because many transit planes, they are available. So connecting planes. So Dubai is a hub of connecting planes. People travel. So if you are coming from the Western countries, most of the times, they have to first land. One of the options is to land in Dubai, and then from Dubai they can move to other countries in the down south. So that is transshipment, that is transit. So it's similar to the transit. So the question is, we must develop constraints for the transshipment points also, so that this cost minimization can be done. And these shipment points are Kansas, Omaha, and Des Moines. These transshipment points are Kansas, Omaha, and Des Moines, 3, 4, and 5. Now, listen to this carefully and pay attention to it. I'm just changing the color of the pen to show you. The principle. What is the principle? Let's write it here. The principle. You also, if you have your notebook, note it down or underline in the book. The principle to do this, to write the equation at transshipment point. The principle is usul, or the method, the rule at each transshipment point is that the amount of wheat shipped in must also be shipped out. That means, so let's write it here. Shipped in, like you remember in inventory. Inventory, we have several methods like first in, first out, last in, last out. You know that FIFO and LIFO methods. Mabada, very good. Yes, Mabada, the principle. So have you heard about FIFO, LIFO? Okay, good. So what happens there? These are methods of inventory where they decide the first raw materials coming will have to go first, or the last coming in will go last. Then there is a method called GIGO, garbage in and garbage out. So garbage is coming in and the garbage is going out. So here, what they do, the rule is shipment in must be equal to shipment out, where at all transit points, shipment points. Meaning, in simple, in a hypothetical sense, suppose this is the Dubai airport and the planes are coming from, I don't know, I'll just try to make one. Okay, so does it look like a plane? Yeah. Okay, Emirates. This is Emirates. So it carries 100 passengers. Okay, from New York, and they are all going to Australia. So they come to Dubai and then they have to again fly back to Australia. So what happens? 100 passengers come to Dubai, and then from here they again have to fly to Australia. So what happens? All these 100, when they fly from here, from Dubai, they have to be the same 100. Otherwise, what will happen? There will be a mismatch, and the flight will be delayed. They have to search for the missing passenger. So the rule is that the number of passengers coming and going should be the same, and they have a waiting time at Dubai. They will have to wait. They may stay there, and then from after the time means when the time is a scheduled time has come, they have to again move to the next flight and go on their destination. So in this process, what we see, there are two parts, one reaching to Dubai and then from Dubai to Australia. The number has to be same, the number of passengers have to be the same, so that there is a match, there is a balance. The same way here, the principle in transshipment is, in order to write the equation, the principle is a shipment in must be equal to shipment out. What does it mean? It means that the 300 which are coming from the two, which are the two centers, new centers, I forgot, Nebraska and Colorado. So from Nebraska, whatever wheat is coming to these centers, we don't know how many are coming right now. That's a question we have to solve. Similarly, from the Omaha, Colorado, the wheat is being sent. We don't know how many tons, but they are coming to these centers, and we also don't know how many wheat is coming to which center. So 600 has to be distributed in the three centers. We don't know how many are distributed. Okay, so it may be 500, 100, 400, 200. We don't know, but we have to write them in the form of equation. So on one side, there are two equations so how many alternative routes are there? There are 1, 2 and 3 routes are there. X13, X14 and X. So at Kansas, it can come from Nebraska or Colorado. What are the options of the wheat coming in Kansas? At Kansas, wheat can come from Nebraska or Colorado. Both the options are there. That means X13 and X23. Both the options are there. Let's look at here. Both the options are available at Kansas City. X13 and X23. This is at Kansas. So this is the ship wheat coming in at Kansas. From where? From either Colorado or Nebraska. From either Nebraska or Colorado, 1, 3 or 2, 3. This is at Kansas. From Kansas, now the rule is, the principle is, this is shipment in. What about shipment out? How are you going to send the shipment? Because here there should be, we have to see that it is equal. Whatever is coming to Kansas must be sent. So at Kansas, the amount shipped out is, again, 3 routes are there possible. We can send from Kansas to Chicago, like last week, we did from Kansas to St. Louis and from Kansas to Cincinnati. So we have 3.6, 3.7, 3.8. 3 possibilities are there. So let's look here. We from Kansas center, which is an intermediate point now. The 3 options are 3.6, 3.7, 3.8. Okay, so we are now having 5 components, 5 possible routes, and the rule is that we have to check, the shipment in must be equal to shipment out. So these two are shipment in, X13 plus X23, and this shows the shipment coming into Kansas. These 3, X36, X37 and X38, are the wheat going out from Kansas. So what is the rule? They should be equal, and this is what has been written. X13 plus X23 is equal to X36 plus X37 plus X38. Why are we making it equal? Because no wheat coming to Kansas should be left. No passenger coming to Dubai should be left. All 100 who came to Dubai must go from Dubai, go out from Dubai, right? So this is the same here in the transshipment. It's the same transshipment. So what happens? Whatever wheat is coming to Kansas must go out from Kansas. That means shipment in must be equal to shipment out. X13 plus X23 must be equal to X36 plus X37 plus X38. What are these? These are the possible routes by which wheat can go, and these are the possible routes by which the wheat can come to Kansas. And then what we do, last point, okay, let me just remove this part so that it's clear. Yes. So what we are seeing here, we wrote the equation first based on the principle that shipment in is equal to shipment out, and then we bring the we make a straight line equation by taking all the variables to one side. So we have the shipment in equations components and the shipment out components. We bring it here. It doesn't make any change. The only thing is we are changing the signs. It plus becomes minus when it comes to the opposite side. So from the right hand side, we are taking all these to left hand side, and now the equation becomes x13 plus x23 minus x36 minus x37 minus x38 is equal to, nothing is left here, 0 is left, so it must be equal to 0. It is the same, okay, it's the same. It means that the passengers coming in 100 minus 100, the result should be 0. So if we don't know how many passengers are coming in, we will say New York to Dubai, and here it is Dubai to Australia. How many passengers are there? X New York to Dubai is equal to X Dubai to Australia, and we take this is plus. So when we bring the Dubai Australia passengers to this side, XND minus XDA becomes 0. So it's the same, okay. So this is how we write the equation for the transshipment point at Kansas. And now, in the book, it has done for others, and we can do it. So now try to do it yourself first for the other one, for Colorado, for the Omaha and Des Moines. Can you do it? Do it fast, please. For Omaha and Des Moines, let's do it fast. At Omaha, the rule is shipment in is equal to shipment out. So we have to follow that rule. Do it first. Let's do it one by one. At Omaha, what happens? The routes are 24 and 25. Okay. So we will write it x24 x. So can you help me in doing that so that I don't have to go back? X24 and x25. We write plus. Right? Now for the this is shipment in SI x24 plus x25. Am I right? Now what about shipment out? What are the possible routes from moving the wheat from Omaha? What are the options? X4. Tell me fast, because don't make it a mess. It's very easy. Just look at the network and tell me what are the how many are there? 3, isn't it? 3 options are there. 2 for coming in, 3 for going out. So let me know what are the options of sending out from Omaha. Here, see, X46, Chicago, St. Louis and Cincinnati. Very good. Good, mashallah, seal. X46 plus X47 plus X48. Okay. Now, what should we do? We will write X24 plus, what is the principle? This should be equal to this. So X24. Why it's not like this for Omaha? X14 and 24. Oh, good question. Okay, so let's look at the network. Why is, let me just remove this all so that it's discard. Very good question, right? So Ruba asks, why is it not like Omaha? At Omaha, Why is it not 1 4 and 2 4? The thing is, we 1 4 and 2. Yeah, it should be 1 4 and 2 4. Yes. What has she done? The two options for coming in at Omaha is 1 4 and 2 4. Here it is x 1 3 and 2 3. X 2 3. You are right, Ruba. Did we make a mistake in the other side? It's x 1 4 and 2 4. Here it is x 1 5 and 2 5. Very good. It's a good find. So we have at Omaha we have x 1 4 and x 2 4. Two options are there. And at at Des Moines we have two options, x 1 5 and 2 5. Okay, good. So let's go back to our screen again. Constant. So for Omaha we have shipment in SI is x 1 4 and x 2 4. This should be equal to shipment out, that is x 4 6, x 4 7 and x 4 8. What should they be as a principal? X 1 4 plus x 2 4 must be equal to how much? X 4 6 plus x 4 7 plus x 4 8. Now what we do, in order to make it a straight line equation, we will write down x 1 4 plus x 2 4 minus x 4 6. This is clear to all. How we move it's becoming minus on the other side. It's easy, when we take this to the left hand side opposite, we can do. It's allowed. It's possible. So when we bring it here, then very good. Yes, Ruba is right. X 4 6, x 4 7, and I request others also to write. Okay, just practice by writing on the WhatsApp group. It doesn't matter how many students write. You write as Ruba has written. Write it yourself. X 1 4 plus x 2 4 minus x 4 6 minus x 4 7 minus x 4 8 is equal to 0. So this is our equation number. How many? 5 and 6, seventh equation, isn't it? We already wrote the equations for 1, 2, 3, 4, 5. These are supply equations. 1, 2. These are demand equations. Demand 1, demand 2, demand 3. And now we are coming to the transshipment equations. So this is transshipment equation number 1. We have the transshipment equation number 2. Now you have to do it yourself, the second one. Okay. So let's do it for Des Moines now. At Des Moines, the shipment in. Right. Let me see if you can do it. We have two routes from where wheat can come to Des Moines. What are those? Good. So we have 1 5 and 2 5. These are shipment in. And what about the shipment out from Des Moines? We can send the wheat to through three possible routes. What are those routes? X 5, x 5 6 and x 5 7 and x 5 8. Okay, good. I think Rahaf has some typing mistake. Please correct it. Okay, look at the network and see from Des Moines. So the shipment coming from Nebraska and Colorado, x 1 5, x 2 5. Shipment going out from Des Moines to Chicago, then Des Moines to St. Louis, Des Moines to Cincinnati, X56, X57 and X58, right? All clear to all of you? What about other students? Okay, it's very interesting, so let's participate. Okay, all right. So now last thing, we'll write the equation for Des Moines also. We will write x15 plus x25 is equal to x56 plus x57 plus x58. Now simply, we take all these on the left side, x15 plus x25 minus x56 minus x57 minus x58 is equal to 0. So this is our transshipment equation number 3. So in total, how many constant equations we got? We got 5 earlier and 2 now. So there should be 7, right? 7. We have 5 here, 3 here, 8. 8 equations are there. Let's look at the final complete model of this problem. Let's look at it very carefully. Okay, and now we don't need to, very good, Asil. Now we will not go back to looking at the model. We'll just understand from the complete model. Okay, so you have to help me in understanding. So what is the minimize z objective function? What is the equation for objective function? 16x13 plus 10x14 plus 12x15 plus 15x23 for 14x24 plus 17x25 6x36 8x37 10x38 7x47 47 48 56 57 58. How many are these? 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. So 15 alternatives are there. Where did they all come from? 15. Who will tell? Who will identify the alternatives? 15 alternatives are there. 15 alternative routes. Where have they come from? And they will all add up to the transportation cost. Where have they come from? They have come from the supply side and from the demand side. So what happens from the supply to intermediate? How many alternatives are there? Supply to intermediate, how many alternatives are there? 6. Very good. And from intermediate to destination, demand, how many alternatives are there? 9. So in total, there are 15 possibilities, and these are there 15. So if we say x13, it is from Colorado, Nebraska to Kansas. What is the cost of transportation? 16. So we, in this final model, after the constants have been identified, now the final model, what happens? 16 is the cost from sending from Nebraska to Kansas, x13. So 16 multiplied by x13, 6 multiplied by x36. So if you count these arrows, these are 15. 1, 2, 3, 4, 5, 6 and 9 here, 15. So what we do, we write down the cost. So this 16x13 means this is the cost of transporting x tons of wheat from 1 to 3. This is the cost of transporting x tons of wheat from Kansas to Chicago, and the transportation cost here is 6, 8. So the final model is taking into account, because this is the cost, this cost. So cost has to be in terms of money. So we are adding the number of tons and multiplying by the cost per ton. X we don't know. So for all these 15, we have added there. Now the question is, we have to use all, because there is an addition from transportation. There is an additional cost. This is given by the company. They have added a new center, 2 new centers, and they say, we have to first move from here to here. We cannot directly go. There is not an option. Okay, so this is not an option. We have to move from 1 to 3 and then to this. So that means there is an additional cost in transshipment, which is the intermediate cost. So that means the cost will be increased, and the complexity has also increased, because earlier it was just 9 choices, now we have 15 choices. Earlier there were just 6 constraints, now we have 8 constraints. So this equation is clear to all. How did we get all this equation? Okay. Then looking at the constraint side, we already derived all of them. These 3 are supply. These 3 are the demand constraints. No, these 3 are supply constraints. 3, 7, 4, 7, 5, 7, and 3, 8, 4, 8, 5, 8. These are from this supply. Demand is from here and supply is from here. This is from the the Nebraska and Colorado supply side. The maximum they can send is 300 and 300. So on the supply side it's 600. On the demand side we have 3 centers. On supply there are 2. On demand there are 3. So there are demand constraints x36 plus 46 plus 56 is equal to 200, 100, 300. And this is what we learned new, how to derive the equation for intermediate points. This we have already derived. So now in total we have 8 constraint equations, and further one more equation is there, one more parameter has been given, the condition, that is the number of tons has to be equal to or greater than 0. It can be less than 0. So this completes the model or the equation for transshipment problem. The transshipment problem. Okay. So we are ready now to move to the solution stage. So we use either computer solution or we use the manual methods. We can do any. That we will learn in the next class. Today we will see another problem which is similar to the transshipment and transportation. Slight difference is there. It's again a network problem, but there is some difference. What is the difference here? I have highlighted is that each source and the demand, like we said, shipment in and shipment out has to be equal in transshipment. But in this problem, assignment, you know what? There is another word, allocation. Allocation. What is the Arabic for assignment? This assignment is not the wajib. This assignment is to give something, to allot, to allocate. So what is the Arabic for assignment? Who will tell? Muhammad. Okay. Rahaf says Muhammad, so I'll write that. Okay. If you have any other word, you can just write. So in this problem, the main issue is to send a delegate or a group to a particular center, and it should be one only, not more than one. That's the condition. That makes it different. So each source and the demand at each destination are each limited to 1 unit. So at the source and the demand, the supply at each source and the demand at each destination are each limited to 1 unit. What does it mean? Let's look at the problem in the book, and we'll do it fast. It's easy, very easy. In the Atlantic Coast Conference, there are 4 basketball games on a particular night. On one night, there is a game to be played, basketball game. The conference office wants to assign 4 teams. So on one night, there are 4 games. So we have to send 4 teams. 4 teams are to be sent on one night in a way that will minimize the total distance traveled by the officials. 4 teams of officials, okay? So there are 4 teams of officials to be sent to 4 destinations. And the target is, the Z is to minimize the total distance, the amount of traveling done by the officials. The supply is always one team and the demand is only for one team. The supply is always one team. From the supply side also it's one, and from the demand side also it's only one. So there has to be one set of official going to the playground, and the demand at the playground is also of one official, one set of officials or one official. So this becomes a challenge, and we have to find out what is the, so these are the game sites and these are our distance. So officials A, B, C, D, these are the people who are to be sent to Raleigh, Atlanta, Durham or Clemson. 4 playing sites are there. So if A goes from A to Raleigh, this is the, the places, supply side, and this is the destination. So if the official A goes to Raleigh, he has to travel 210, then Atlanta is 90, Durham is 180, Clemson is 160. B is 170, 130, these are the distances. C, D, all distances are given. The question is, like, if we look at A, the minimum is 90, but we have to make a chart, make a model so that the total distance is minimized. Total distance is minimized. So the linear programming formulation of the assignment model is the same. We do the same. Like, we have A, B, C, and D, 4 supply centers, and we have 4 demand centers. We may say D1, D2, D3, and D4. These are, and the possibilities are the same. We have 4 possibilities here, 4 each here, so 16 possibilities are there. But here the thing is, out of 16 possibilities, we have to choose only 4. Only one option for each, okay? Only one option for each. It cannot be more. So that's the difference here. A can go only from point A to D1. A may be, we may say A is a person. So this is person point A, B, C, D. So A can go only from A to D1 or D2 or D3 or D4. And at D1 also only one person is required, or one set of officials are required, not more than one. That is the main difference here. In case of other problems that we saw the quantity was 300 or 200, but here the unique nature of this problem is that the quantity required is only one, and the quantity supplied is also only one. So that is the unique nature of the assignment problem. One on the supply side, one on the demand side. So how do we write it? We first of all we write the supplies, the minimization function. So we have demand, the distance XAR. This is the number of this is the distance traveled. Number of people XAR. This is the number of person from X to AA. XAR, I mean, they are calling it by the name of city. So let's say this is R, this is A, this is D, and this is C. Okay, we'll do it that way so that it's clear to all. A, B, C, D, and here the cities names are R, A, D, and C. So what are the choices? So this is the number of people. X, we don't know how many will go from which person will go from which center. Okay, so X can go from A to R, can go from A to A, from A to D, or from A to C. So it is XAR plus XAA plus XAD plus XAZ. But what is the condition here? The condition is 1 only. All together they should be equal to 1, and Xij is also greater than equal to 1. It's very interesting to see that X cannot be can be only equal to or greater than 0. That means it may be 0 or 1. What does it look like? If you look at it logically, we have 4 options: 1, 2, 3, and 4. Now A can go or one person can go from A to R, A to A to D, A to C. But it says that only one it has to be equal to 1. So what does it mean? It means that 3 options will be cancelled. You are understanding? In every possibility, in every possible alternatives, 3 options will be cancelled. You understand? That's the interesting thing, isn't it? A, B, C, D are suppliers, so Ruba is right. So that's the interesting point here, that we have to write the equation for all. We don't know which route the official will travel from, okay, from and to. But by looking at the equations, we know that the official will travel only from one route, and the rest of them will be cancelled in all other cases. So it's the same for all. It's for A, B, C, D. Okay. So AR plus AA plus AD plus AC is equal to 1. BR plus BA plus BD plus BC is equal to 1. Then CR, CA, CD, CC. Okay, and then DR, DA, DD, DC. All of them are 1. Okay, so these are the constraints, all constraints. How many are there? We have 1, 2, 3, 4, 5, 6, 7, 8. 8 constraints are there. Okay, so all of them are equal to, when we are formulating the model, all of them are equal to 1 or greater than 0. This is the difference from the other problems. Okay, so till here we saw 3 types of problems. One was the transportation method. That is the most applicable in case of businesses, that we have to transport from one place to the other. The second is there is a distribution center or an intermediate point in between the two. And finally, there is assignment, where in sports, in exam duties, we have 4 invigilators and there are 4 examination centers, and we have to send the examiners from one point to the other. The condition is that every examination center we have to send 1 invigilator, and we have 4. We have to minimize the distance also. Okay, so the last problem. Now let's come to the solution part. We'll do the solution next week. It will take good time to understand the 2 methods. On one hand side, we see these are the manual methods: MODI, least cost, northwest, and Vogel's approximation. We'll see them in the next week in detail. And on the other side, there is a computer solution in which has been explained in the book in detail. But I am not touching this because we need that software to do that, and means an expert. And if you want to, this is your choice. If you want to learn during this semester, you can take up a course. There are many courses available, or we can practice on our own. So if you want me to engage, I will not mind explaining this or learning it outside the curriculum, outside the syllabus. But for all students, we will use the manual methods to solve the problem. But you are free, you can tax me by engaging outside the syllabus, and we can do it. We can keep learning the computer solution also, no problem. So how to solve through using the Excel? We need solver or Excel QM to solve this. The method is given in the book. You can read it. The manual methods are not given in the book. Modified distribution or least cost or northwest and Vogel's approximation methods are there. What they are and how we use them to find the minimum cost, that we'll do in the next class. But before we end today, we'll end with a case study, a small example given in the book regarding the use of transportation method in business, how it saves the cost and how is it applied. So we'll take 5 minutes to complete this and then stop. So this example is given in your book. that United States Postal Service, the UPS, has one of the most complex transportation networks in the world. It annually delivers more than 200 billion of pieces of mail. And now, you will be able to understand how it is taking the shape in a model, because we know all the components, we saw the transportation problem and the network. So when we read the problem, I think the image will be created in your mind about the network, isn't it? So USPS delivers various types of mail. Mail means the letters, posts in different shapes, weights and sizes through intermediate points and facilities. So this means what type of a problem are we dealing with? Transportation, transshipment or assignment? Tell me. Very good. So we are dealing with transshipment problem in this example. UPS or USPS, normally they call it United Postal Services. Across the world they have their services. It's called UPS. This is a transshipment problem they are facing using various modes of transportation. On average weekday, the UPS highway transportation network alone will include more than 75,000 trips. In our case, we had just few routes and few trips, but here you see the quantum of services is very huge, between more than 30,000 facilities. We saw 2 and 4 facilities just now in the examples, but in real life, when the business is so big, Amazon is even bigger. They have 30,000 facilities. UPS transportation analysts use management science. So you see, these are the people inside the business, inside the company, who are responsible for doing this, who are management science experts, who will find the best solution for the company to identify cost-saving opportunities in its highway transportation network. So one model, they created a model based on the transshipment, which is called the highway corridor analytic problem, optimizes the selection of trips between facilities. Okay, so it's the same that we learned just now. Selection of trips between facilities, which route should be followed to minimize the total transportation costs subject to delivery requirements. So how have they created this model? The models include originating facilities, pickup times, destination facilities, delivery times, delivery volume, whether or not the delivery can be split, stops between the origins and destinations, transportation capacity, and the variable transportation costs. So you see here, it's in the real time life situation, it is becoming very complicated. So manually, it's not possible to be done. So modeling also, we need softwares, as we learned in the computer solution chapter. So we will have to use some sort of good software to help us create the model. As we did just now, it was a manual modeling. We did it manually. We created all the equations ourselves. But when we have so many variables, so many constraints, then it may not be possible for us to do the modeling ourselves. We will need the computer programs and also experts who can write the programs. The model identifies existing and potential new trips that can possibly transport the mail from an origin to destination, including stops. That means the intermediate points, the transshipment points. Thus, the model includes 0 and 1 decision variables. That is, if the trip is selected, is 1. If it is not selected, it's 0. So this is a unique thing. There is we can say it's more looking like a probabilistic scenario, where there are now the model has to decide that if this trip is selected, you have to choose 1. If the trip is not selected, you have to automatically make it 0. So this is a we can say intelligent model we are selecting, which can switch on its own. We don't have to switch, rather it will do it on its own. And so the model includes 0, 1 if the trip is selected, if 0 if it is not, and real variables that indicate the proportion of a delivery's volume that is routed using a specific trip. The model solution identifies the optimal set of trips, that is what we learned all about in the transportation, that satisfies the delivery requirements, all the delivery requirements that we saw from here till here. The HCAP model, so you should remember this, learn more on it, try to find more details on it. Also, when you will read cases on HCAP, you will see more recent, like Amazon's transportation, etc., to see how the transportation model, what we learned in book, has been applied in business, in reality. So it has saved UPS more than $5 million in annual transportation cost savings. It's a huge cost saving, and that is the purpose why we are learning this course, to make the best decision to utilize the resources in the best possible way. So that's it for the three types of examples and the theoretical aspects and the modeling of networking problem. Now, next week we will solve the problem and find ourselves the minimum transportation cost possible. Okay, so we'll take up an example, two examples, or one example and one I can give you for assignments, and then we'll do it ourselves. So it will be much more interesting. I hope this was interesting.